Question 2 says, suppose we take a rock of mass m and throw it into a black hole. What is the change of energy of the black hole? When the rock goes into the black hole's mass will change according to the rock, right? So we change from the black hole's mass of m to m plus q, q being equal to mc squared, or the energy of the rock from Einstein's equation, E is equal to mc squared. But what is the corresponding change in temperature and the heat capacity? So we know that q is equal to mc delta T, but q is also equal to E equals mc squared. So we can actually equate these two, making mc delta T equal to mc squared, and solving for delta T, we obtain q over mc, or mc squared over mc. These c's are different, so keep that in mind. The specific heat is also equal to q over m delta T, which is equal to mc squared over m delta T. In lecture, we also mentioned that one way to define temperature is 1 over T is equal to ds over dE. Plugging in these equations with respect to m, we obtain the equation ds is equal to c squared over t dm. And from this, we can actually take the integral of this equation in order to get s is equal to 4 pi gkn over hc times m squared. So this integral isn't actually that hard to solve. Here's the work for it. The main problem a lot of people have with this integral is the fact that we transition from step 1 to step 2 so drastically. We transition from a simple fraction to a fraction that results in multiple variables and a seemingly impossible substitution. However, if you recall from earlier in the problem, we state in the background for Hawking that the temperature of a black hole is equal to hc cubed over 8 pi gmkb. This entire equation itself can be transferred over to our integral, as if you recall, our denominator is tbh, allowing us to substitute in this entire equation here, canceling out the c and simplifying the fraction entirely. So from there, we do our simple integral to get our final result. Again, like this week's first problem, I don't have any problems that you can necessarily practice to be better at these types of problems. It's more or less just a concepts check with substitution. And overall, it's a very difficult problem in a sense because it's very abstract and there's not really anything to base it off of. It's not like a normal physics problem that we'd find in the textbook. I definitely recommend watching everyone else's explainer videos if you need more help understanding this problem. Anyway, that's all for me for now. Thanks for watching.